Welcome back. Last time we talked about sequences, and today we're going to talk about geometric series. This is in section 8.2 of our textbook. And I haven't even really, I don't think, told you what a series is yet. It's different than a sequence, but related. But I want to start by looking at an example. In this example, there's a patient that's taking some medication. So a patient takes a 100 milligram dose of a medication every 8 hours. And each time the drug is taken, the body absorbs it, but over time, some of that medication is excreted and leaves the body, but some of it does remain. A portion of it will remain. So assume that 40% of the drug remains in the bloodstream after each 8-hour period. So let's see if we can wrap our head around what exactly is happening to that 100 milligram dose. So we'll call it dose one, and we'll assume that the patient took it like at midnight. So we're going to get 100 milligrams, and the time, we'll call it 0 o'clock midnight. And then we want to know kind of over the course of the next day or two what is happening to the concentration of that medication. So by the time 8 a.m. rolls around, there's only 40% left, so only 40 milligrams are left. And then by the time, let's see, 4 p.m., that's 8 hours later, then there's only 40% of this left. So 40%, so it's decaying. And so 40% of 40 milligrams is 16 milligrams. Then 8 hours later is going to be midnight of the next day. And now we have 40% of this 16 milligrams left, and that will be 6.4 milligrams. And then by 8 a.m. on day 2, we've got 40% of the 6.4 milligrams, and that will be 2.56 milligrams. And let's just do one more iteration. By 4 p.m., we've got 40% of this amount. So it's really getting out of the body, but there's still some there. And 40% of 2.56 is 1.024 milligrams. Okay, so this is what's happening to that dose over time. But in the meantime, when 8 a.m. rolls around, there's actually a second dose that happens, right? He takes another 100 milligrams. So dose 2 happens, and he's going to, at 8 a.m., he's going to take 100 milligrams. And then by 4 p.m., that 100 milligrams is down to 40 milligrams. And it follows that same pattern, where every 8 hours, there's only 40% left. So you can kind of think of, okay, at this time he had 100 milligrams, but wow, at 8 a.m. he actually had 140 milligrams in his system because of that new 100 milligrams, but there was still 40 milligrams happening. Well, by the time 4 p.m. rolls around, he's actually going to take a third dose of 100 milligrams, so he'll have accumulated, a little bit that he's retained from that first dose, and some more that he's retained from the second dose and his new third dose. So we want to kind of take a look and see what that looks like. So dose 3 happens at 4 p.m. and he's going to take his 100 milligrams, and it's going to decay over time. Okay, so we're getting an idea of what all of these doses are doing. The question is, with medication, you want to make sure the patient is getting enough, but you definitely don't want to get the medication to toxic levels and have too much accumulate in his system. So it's very important that we know, okay, is this just building forever? Is he going to get way too much in his system? And do we need to modify the dosage? So let's see, dose 5 is going to happen at 8 a.m. the next day. And then we'll do one more dose. Dose 6 is 100 milligrams at 4 p.m. the next day. So we kind of want to see what is being accumulated in the patient's body over time, and is it possible that too much is being accumulated? So what we become interested in is the sum of all of these doses and what's being retained each time as time goes on. Should he keep taking these 100 milligram doses, or is it just going to start accumulating too much in his system? Well, if we add these up, at midnight he's got this 100 milligrams. At 8 a.m. he'll have his 140 milligrams in the system. And if we add up these guys, he's got, at 4 p.m. he has 156 milligrams. At midnight of the next day, if we add up all of these, he's going to have 162.4 milligrams. And if we add up these guys, at 8 a.m. he will have 164.96 milligrams. And then at 4 p.m., he's got little pieces of all of these doses plus his new fresh dose, and he will have 165.984 milligrams in his system. So an important question for this patient is, we need the drug to maintain certain levels in the body to help the patient. It has to have a therapeutic effect. If you don't have enough of it, it's not going to elicit the change that we want in the body. But on the other hand, we do not want the medicine to accumulate to toxic levels where it could start hurting the patient in a really bad way. And so the question becomes, how do we know, what is being accumulated over time? If he has to take this medication, or they want him to take this medication for years and years and years, is it possible that it would reach toxic levels? This is a really important question. You think of the millions, billions of people who take medication, and these types of questions are very important. Okay, so we're going to pause on this example for right now, and I want to talk about some kind of general theory of the idea of a series, and then we're going to come back to this question. Okay, so we've already talked about what a sequence is in the last section, last video. It's just this ordered set of numbers, and it usually goes on infinitely, and they typically have some pattern to the numbers. Maybe you're adding 5 each time, or maybe you're multiplying by 2/3 each time, or maybe it's some kind of slightly more complicated formulas. There's a whole variety of ways you can generate sequences. Well, a series is related to a sequence in that you take up all those terms, the A1, A2, A3, forever, and you just add them up. So you can see how this relates to the last example, where we would be interested in, the accumulation of all of those doses, and at a specific time, what remains in the body from each dose. So series are just, you're taking a sequence and you're adding up each of the terms. So we're going to go kind of wide right now, and we're going to think of the whole set of any type of sequence or series. All of them are in this big group, and there's a lot of different types. I'll just tell you the names of a few common ones: arithmetic sequences and series, P series, alternating series. There's ones called telescoping sequences and series, harmonic. There's the famous Fibonacci sequence. But there's one that we're going to really concentrate on. It's a large class of sequences and series. And of course, I should say that there's plenty of sequences and series that don't even have names. You can generate them any old way that you want to. But a large class of sequences and series that we're going to hyper-focus on, are geometric. So the things that we're going to talk about for the remaining portion of this section really have to do with geometric sequences and series. Later, we'll talk about some of these other guys. But for this section, we're really honing in on what a geometric sequence and series is. So you may already know this from previous like algebra classes. A geometric sequence is one where each term is obtained by multiplying the previous term by a fixed ratio. So you're just multiplying by this same number each time to generate a new term. Each term is obtained by multiplying the previous term by a fixed ratio. So some examples would be like 1, 2, 4, 8, 16, 32, 64, and on, where we start with the number 1, but to get to the next term, we just multiply by 2, and to get to the next term, we multiply by 2, multiply by 2, multiply by 2. So we have this fixed ratio of 2 in this sequence. And another example would be 5, 5/3, 5/9, 5/27, 5/81, and so on. So this also is a geometric sequence where we started at the number 5, and to get to each term, we're multiplying by 1/3 each time. So multiplying by that common ratio of 1/3. Another example would be the sequence 10, -1, 0.1, -0.01. This also is a geometric sequence. We start at 10. To get from 10 to -1, we have multiplied by -1/10. And then to get from -1 to positive 0.1, we've multiplied again by -1/10. So here this common ratio is -1/10. Here the common ratio was 1/3, and here the common ratio was 2. You can pretty much start on any number, but once you have your common ratio, to get to the next number, you always need to be multiplying by this guy. And so to get any term, like we call it the a-nth term, you have your starting point of a, and you've multiplied it by n minus 1 powers of r. So this is a general formula for the nth term of a geometric sequence. Okay, so think about this right here. This number 8 right here is the 1, 2, 3, 4th term of this geometric sequence. So we should have obtained it by the 4th term needs to be the first term, which was 1, times r to the 4 minus 1. And our common ratio is 2, so a to the 4th equals 1 times 2 to the 3rd. That does equal 8. That was our 4th term. So always the starting point, and then you're going to take n minus 1 powers of your common ratio. This makes sense because the very first term, you only have your starting point. You don't have the common ratio hasn't been multiplied yet on your first term. That's just your starting point. But by the time you get to your second term, you've multiplied for the first time your common ratio. Okay, so this formula is good. It tells us what a geometric sequence is, and we use it somewhat, but it's kind of, at this point, it's just going to be more kind of common sense than a formula that we use necessarily. Okay, so a geometric series, which is related to a geometric sequence, is obviously just when you take all those terms and add them up. So a geometric series is the sum of all those terms, AR to the n. And so a few good questions that we want to ask with a geometric series are, okay, what is the sum of the first n terms? Like, say we needed to add up the first 100 terms or the first 200 terms. Is there a way to find that quickly? Another good question is, what is the sum of all the terms? So if this is an infinite series, is there a way to add up all the terms? Will it always just equal infinity, or is it possible that the sum of an infinite list of numbers could actually equal a finite number? And so these are good questions that we're going to address right now. Okay, let's start with the finite example. We're going to take the sum of just the first n terms of a geometric series. And so that series would look like, you start with your a term, then you have a times r plus ar squared, remembering that each time we're just getting the next term by multiplying by that common ratio. And then the nth term will be ar to the, now we have to think, what will the power on r be for our nth geometrics, and the first n terms of our geometric series. So should it be n or should it be something else? It's definitely not n, because that would be too many. By the time we got to the second term, we only had one r. By the time we got to the third term, we only had two r's. So our nth term will have n minus 1 powers of r. So this is, all laid out, the geometric series of n terms, the sum of those first n terms. We don't want to have to add up, each one piece by piece. So we're going to invoke a sort of trick here. So if we need the sum of, say, the first 76 terms, we do not want to have to add up 76 numbers. We don't have time for that. We want a shortcut. And so the trick that we're going to use here to come up with a sort of closed formula is we're going to take this, listing of what Sn is, and we're actually going to multiply it by r and do a subtraction. So you'll see what I mean. But I'm going to look at r times all of this. So r times S of n will equal, that just means each term gets multiplied by r, so that'll equal a times r plus ar squared plus ar cubed plus ar to the fourth plus ar to the fifth. And then our last term will be a times r to the n. So all I did was I took s sub n and multiplied it by r, so each term is going to get an extra r. And now we're going to subtract this from the top line. So the top line is s sub n, and we're going to subtract this newly constructed second line. And the reason that this is helpful is because when you take this minus this term minus this term will create a 0. They cancel out. This term minus this term creates a 0. They cancel out. This term minus this term creates a 0. This term minus this term, and so on. There's a term here that will cancel with this one. This term will cancel with a term right here. The only things left are actually this initial a and this last a times r to the n. So when you do this subtraction, you have all that's left is a minus the ar to the n. So again, you're taking this minus this, and a bunch of stuff just cancels out or goes to 0. And you're only left with this a minus this a times r to the n. So that's super helpful, because then we can kind of manipulate this formula. We'll factor out an s sub n, and then divide both sides by that 1 minus r. So s sub n equals a, I'll just factor out an a also, over 1 minus r. The reason this is helpful is we now have a closed formula for the sum of the first n terms in this series. All we needed to know is where we start, what the common ratio is, and how many terms you want to add up. And so we don't have to go through this plus this plus this plus this plus this plus this. We can just say, okay, here's your formula. So this now becomes a, we'll say, fairly useful formula. that we'll use to find the sum of the first n terms of a series, a geometric series. Okay, let's look at an example, just practice using this formula. Let's say find the sum of the first 76 terms of the geometric series 3 plus 2.4 plus 1.92 plus 1.536, and it goes on and on and on. Okay, they do tell us that it's a geometric series, so we're guaranteed that. And we have the first few terms, and so we can find the common ratio. The common ratio will always be, in a geometric series, you can just take any two consecutive terms and take their ratio. So you would take like 2.4 divided by 3. This will give us our common ratio. We obviously could have taken 1.92 and divided by 2.4 also. That too would have given us the same common ratio, and it's 0.8. Our a is our first term, which is 3. So between this, and knowing that we want the first 76 terms, this is our n, we have everything we need. So s of 76 will equal 3 times 1 minus 0.8 to the 76th power. And that's going to be all over, let's see, 1 minus r, so 1 minus 0.8. And I'm just going to take a stab before I actually calculate this as to what the first 76 terms might add up to. We've got a 3, 5-ish, 7-ish, 9-ish. Everything's getting smaller and smaller. I'm going to take a stab and just guess that it may be around 16. I have no idea if this is actually accurate, but that's just my gut feeling that this is the first 76 terms might add up to something close to 16. Okay, and the actual calculation of the first 76 terms is 14.999. Really, it should be rounded to 15. But yeah, that was actually pretty close to my guess. I just knew that these terms here were going to get smaller and smaller and smaller and just not contribute all that much by the time you got to the 76th term. But that's way better than having to actually add up 76 numbers together. So geometric series are nice in that way. This is a great formula to find those first n terms, the series of the first n terms of a geometric sequence. Okay, the first n terms, being able to add up the first n terms is pretty good, but what about all the terms? Like what if we wanted to, so what about adding up all the terms, like the infinite number of terms? Can you, this question keeps coming back, can you add up an infinite list of numbers and actually get a finite sum? And yes, the answer is yes, you can. And when does that happen? So we know that, the sum of the first n terms will be a times 1 minus r over 1 minus r to the n over 1 minus r for a geometric series. And what we're really now interested in is what is the limit, finding the limit as n goes to infinity. So the first case we're going to look at, case 1, is when our common ratio, the absolute value of our common ratio, is greater than 1. So in this case, that sum here, let's just look at each piece. We have an a times 1 minus r to the n over 1 minus r, and we're really interested in the limit of this as n goes to infinity. What would happen to this expression? Well, some of these things are just fixed, like 1 minus r is not going to change at all as n goes to infinity. And a is just a number. It doesn't change at all as n goes off to infinity. But this numerator here becomes really important. Like what is happening to this if the absolute value of r is greater than 1? So r could be 2 or r could be negative 5. And n is going off to infinity. What's happening to this numerator? Is it getting small? Is it getting big? And I think we can all see that with an r greater in absolute value than 1, as n goes to infinity, this numerator gets larger and larger in absolute value. Sometimes it could be positive or negative, but in absolute value, it's not getting smaller. It's not converging to anything. This is really getting larger and larger. And so if these two things are fixed, then as n goes to infinity, this whole expression in absolute value is going to get larger and larger. So this whole thing becomes larger and larger in absolute value. And so this expression will not converge. We cannot say that it will converge, so it diverges. So for a common ratio that's bigger in absolute value than 1, a geometric series will diverge. It will not converge. Okay, so we'll put this to the side for a minute, and we're going to talk about case 2, which becomes important. So in case 2, this is a geometric series where the common ratio is actually smaller than 1. We want to look at what could be happening there. So we still have our a times 1 minus r to the n over 1 minus r. This is just the sum of the first n terms of a geometric series. But now we want to think about, well, what if n goes to infinity? What would happen to this expression? Again, this is still fixed here. The a is fixed. It's not changing at all as n changes. This is fixed. But as n gets larger and larger and larger, what happens to this expression? Well, our common ratio is a number smaller than 1. When a number smaller than 1, like say 0.7 or 1/2 or 0.2, is raised to higher and higher and higher powers, a number whose absolute value is less than 1, this expression here, as n goes to infinity, goes to 0. I hope that that's fairly clear to you, and that's not a big surprise. I'm sure you've seen that type of thing before in a math class where a number smaller than an absolute value than 1, as it's raised to higher and higher powers, that will go to 0. Well, that simplifies a lot of things for us, because then this whole expression here, we have the a, we have the 1 minus r, we have the 1, but this guy is going to 0, so he's disappearing as n goes off to infinity. So we can say that the sum of all the terms of this geometric series is a times, there's a 1 in the top and a 1 minus r, but usually we'll see this written as a over 1 minus r. And what a beautiful, elegant formula for something that's infinite. I mean, this is super useful. So you have this infinite geometric series where the common ratio in absolute value is less than 1. And if you know the first term and the common ratio, you can determine the sum of that infinite number of terms. This is very useful. And so this we should say, oops, this is if that common ratio is less than 1. That's an important piece of this formula. We are very excited about this formula. When that common ratio adheres to this restriction, we can find the sum of those infinite terms. When it doesn't, it's not that great. It just diverges. Not very exciting, but this is the exciting part, that we now have a closed formula for the sum of those infinite terms. Okay, so now we're going to go back to that example that we started with, where we had a patient. The patient was getting a 100 milligram dose of a medicine every 8 hours, and we knew that 40% of that medication remained in the system, the patient's system, after each 8 hours. And then every 8 hours, it would be, at this type of reduction. So the question is, what is the drug concentration as n goes to infinity? They say this patient has to be on the medication for the rest of his or her life, and what is going to happen to the concentration of that medication in his system? This is sometimes called a steady state drug concentration. And so we're really looking at, the 100 mil. You can kind of remember, so back here where we were adding up all of these, the doses and the doses that were remaining, we need to think of this as this infinite list. What if it just kept going? We're taking a bunch of the separate dosages and the concentration that's left, but just extending it out to infinity, so forever. We want to know what that all adds up to. So that would mean 100 milligrams plus 40 plus 16 plus 6.4 plus 2.56 plus 1.024. But we don't stop there. We just keep going on infinitely. We want to capture all of the little fragments of doses that are being retained in the body. And so we could also write this in summation notation. N equals 0 to infinity. Our first dose was 100, and then we're multiplying by 0.4 each time. N is the right term here because we'll start with n equaling 0. So our very first term will just be 100 times 1, and then we'll add 100 times 0.4, which is this 40, and 100 times 0.4 squared, which is the 16. Okay, the awesome thing is this is a geometric series with our common ratio in absolute value less than 1. So we have this fantastic formula that tells us exactly what all of these infinitely long list of numbers will add up to, and it's equal to a, which is 100 over 1 minus r, which is 0.4. You literally cannot get a more elegant formula than this. You're adding up an infinite number of things, and all you need to know is where you start and what you're multiplying by each time. And so this ends up being 166.67 milligrams. The levels of the medication will not go over this. So we'll say that doctors deem this safe. It's enough of the medicine to invoke some change for the health of the patient, but it's not so much that it becomes toxic. So that's a very important question to ask, about the accumulation of drug concentration, and geometric series help us answer that question. Okay, we need to give some sort of general definitions about what it, and more formal definitions about what it means for a series to converge and diverge. A series converges if the sequence of partial sums of its partial sums, S sub n converge. So last time we talked about what it means for a sequence to converge. Well, a series converges if the list of its partial sums as a sequence converges. So you have the sum of the first term, the sum of the first two terms, the sum of the first three terms, the sum of the first four terms, and so on infinitely. If this sequence of partial sums converges, then we say the series converges, and a series diverges simply if it does not converge. So if it is not convergent. So let's look at some examples of sequences and series, just so that we can get kind of a feel for how all of this relates in the context. Okay, we'll take the most basic sequence to start with, the sequence 1, 2, 3, 4, 5, 6, and it keeps on going infinitely. This sequence definitely does not converge. It will diverge because it never zeroes in on one particular number. It just keeps going on, in this case, infinitely large. The corresponding series, if you're going to add up all these terms, well, they're just going to get larger and larger, so it also diverges. The next one we look at is this sequence 1, -1, 1, -1, 1, -1, just on infinitely, just alternating between these two numbers, positive, -1. And the sequence, even though it doesn't go off to infinity, it never zeroes in on one particular number. And so in this case, we also say that the sequence diverges because there's never one number that it gets closer and closer and closer to. It just keeps flip-flopping between those two numbers. If you think about what the series is doing, the series would look like 1, and then we add up the first two terms, we get 0. We add up the first three terms, we get 1. Add up the first four terms, you'd get 0. Add up the first five terms, you'd get 1. This is what the corresponding series is doing, and so it also diverges. It never gets closer and closer to one particular number. So this diverges. Okay, let's try to find some things that start converging. Okay, this sequence is just 1, 1/2, 1/3, 1/4, 1/5. It's a type of harmonic sequence, and this sequence is going to 0. So we can say that this sequence converges. Interestingly, though, if you add up all of these terms, 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5, and keep going, this does not converge. The sequence of partial sums does not converge. And so while the sequence does converge, the series keeps on going to infinity, so this diverges. This sum goes off to infinity. One important lesson from this is that if a sequence converges, it doesn't necessarily mean that the corresponding series converges. So converges to 0 and diverges. This is another sequence, and I haven't written it out like these guys, but this is describing a sequence. This sequence is definitely related to this harmonic, but it starts at 5 instead of, this one technically starts at 0, I guess. So this sequence described here, it will converge, and this one converges to 5 and goes off to infinity. Then the sequence gets closer and closer to 5, and the corresponding series, for similar reasons as above, it diverges also. This sequence here, you can kind of see what's going on. It's always 1 over n squared for each term. This is not a geometric sequence. It's what's called a p-series, and well, this series is called a p-series, and we'll talk more about this later. But this sequence, you can tell the numbers are getting smaller and smaller. This will converge to 0. And if you added up all of these terms, so you took them and added up the infinite list of terms, the infinite list of terms actually will converge in this case, and it converges to 2. So this is the first series we have where it converges to 2. I haven't explained why. Why does this one converge, but this one doesn't? We'll talk more about that question in the next few videos, but this one does converge, this one diverges here. Okay, we have not in any of these examples yet talked about geometric sequences and series, so let's take a minute and look at some geometric. Say that we had the sequence 3, 6, 12, 24, 48. So this is a geometric sequence where a equals 3 and r equals 2. We know that this, well, you can tell that the sequence is getting bigger and bigger, and the series will not converge either. Our common ratio in absolute value is larger than 1, so that's a big problem. So both the sequence diverges and the series diverges. What if we had the geometric sequence 8, -2, 1/2, -1/8, 1/32? So this is a geometric sequence, and our a is 8. And our common ratio, you can probably tell, you could take this guy over this guy, is -1/4. We can tell that the sequence itself is getting closer and closer to 0. So the sequence will converge to 0. And the corresponding series will converge also because we have this awesome common ratio that in absolute value is less than 1. So the series will converge to A, which is 8, over 1 minus our common ratio, which is -1/4. This is 8 over 5/4, which is 32/5. So that's 6.4 or 32/5. If you add up all of these terms here, infinite long list, you'll get 6.4 or 32/5. So I guess a few things that we're seeing is that it's a little bit easier for a sequence to converge than for a series to converge. That totally makes sense because a series, you're adding up terms. So just by that nature, it's getting bigger and bigger, and it is going to have a harder time just settling in as a sum, as a series of sums just on one number. We see that even if a sequence converges to 0, a series could still diverge. The 2 times that the series did converge, the sequences did converge to 0. That's no accident, but it didn't guarantee, if a sequence converges to 0, it didn't guarantee that this series would diverge. So this is going to lead to an important theorem that's called the divergence test. So the divergence test, it was hinted at by what we just looked at. If you have a series, so this is a series that converges, then the corresponding sequence, so this is just the limit as n goes to infinity of a term. So this is representing what's happening to the sequence as n goes to infinity. That sequence has to be approaching 0. So I guess one way to think about this is if a sequence diverges, then for sure the series diverges. There's no way for a series to converge if its sequence diverges. If a sequence were to say converge to 5, the series will always diverge. If you're a sequence and you're converging to a number that's not 0, your corresponding series cannot converge because in essence that sequence, you're adding up a bunch of terms and each term is getting, closer to the number 5 maybe. Well, you're adding up 5 an infinite number of times, so the series will never converge. So the sequence converging to any number but 0, the series will diverge. And the last thing we can say is that if a sequence converges to 0, then what do you think? Can we say that the series converges? No, we can say that the series may or may not converge at this point. So the series may or may not converge. This condition of the sequence converging to 0 is a necessary but not sufficient condition for the series to converge. So if the series does converge, then you know that the sequence converged to 0. But you don't necessarily know a series will converge just based on a sequence converging to 0. Okay, we're going to look at an example. We're going to use geometric series to answer this question. Write the repeating decimal 0.12121212121212. So this little bar right here, which should only be over the 1, 2, is just telling us that the 1, 2 gets repeated infinitely. But we're going to write this repeating decimal as a rational number. I don't know if you remember this fact, but if you ever have a decimal that repeats, it is able to be represented as a rational number. That's just a fact from math. And so we'll use geometric series to make this happen. So 0.1212 repeating is the same thing as 0.12 plus 0.0012 plus 0.000012 plus we could just keep on going and adding those terms. So we just need to decide what A is. A equals our first term. And then our common ratio. Well, what was it that we were multiplying from here to get to here? And it is probably 10 to the minus 2. So 1/100th. If you take 0.12 and multiply it by 1/100th, you'll get this term. If you multiply this by 1/100th or 10 to the minus 2, you'll get this term. So this is our common ratio. It's definitely less in absolute value than 1, so we should be good to be able to find the sum. And that's going to lead us to being able to write it as a rational number. If you're ever not sure on what the common ratio is or you just want to double check yourself, you can always take a term like 0.0012 and divide it by the previous term, and you'll see that that checks out, that this is the common ratio. So that means that the sum of this infinite series is A, 0.12, over 1 minus 1/100th. And so we want to write this as much as we can in fractions so that we can get a rational number as a solution in the end. And this, so we'll write this as 12 100ths in the numerator over 1 minus 1 100th is 99 100ths. And then that becomes 12 divided by 99. That is the rational way to express the number 0.12121212. So the way we found it out was using a geometric series. Before we end this section, I want to give a few notes on summation notation. This is the way our textbook uses or writes geometric series, where you have a r to the n, and we're going to start at n equals 0 to infinity. This will generate, you start at n equals 0, and then we get a times 1, then you go up to n equals 1, a times r to the first, n equals 2, a times r squared, all the way to infinity. And so this is a representation of a geometric series. Some textbooks or some places online will use this representation of a geometric series. And are these the same thing? This and this, where here we have an a to the r n minus 1. Why is it n minus 1 all of a sudden? Well, they're just starting their counting at a different place. So it definitely is the same thing. If you were to write this out, you would have a to the r 1 minus 1, which is just 1 or 0, and then r to the 0 is 1, plus a to the 2 minus 1, so ar plus ar squared. It generates the same thing, just counting, indexing just a little bit differently, and so this looks a little bit different, but definitely the same result, same thing you're going to get out. These are both representing geometric series. And one last example I wanted to look at that might be helpful in the homework. Write this numbers, 24.72341, so we get a repeating 341 over and over again. As a geometric sequence, use summation notation. So here we do have this repeating decimal, but we've got some junk in front of it that we have to kind of take care of, and then they want us to write it in summation notation. So the way to handle this is kind of separate the initial stuff from the repeating part. This is 24.72 plus, let's see, 0.00341 plus 0.2345341, and then we are going to keep getting that repeating 341. We had some initial stuff, and then we see where the geometric series kicks in. And so we could write this using summation notation as 24.72, and then invoke the summation notation where we have n equals 0 to infinity. The initial value is 0.00341. And then to get from one term to the next, it looks like we're multiplying by a 10 to the negative 3. That's our common ratio. If you're unsure, again, you can always take a number and divide it by the previous number to get that common ratio. And we definitely still need this n. This is how we write it because we're starting at n equals 0. So this is a way to write this decimal number as a geometric series using summation notation. I want to take a minute and just kind of look back on things that we've learned here in this section and a few things that are coming up. One thing we started off saying was that geometric series are an important type of series, but they're certainly not the only type of series. There's all sorts of, we looked at a whole conglomeration of different types of sequences and series, but this is where we concentrated on geometric series, and they are pretty important. Any geometric series, if you want to add up the first n terms of this series, you do not have to manually type in n numbers into your calculator. You can use this formula. It works for any geometric series. The common ratio could be anything, smaller than 1, bigger than 1. It doesn't matter. This will always be a formula for the sum of the first n terms of a geometric series. And then we learned if you have the very special condition where your common ratio in absolute value is smaller than 1, then the infinite list of terms will converge, and we have a really nice formula for the exact number that they converge to. So next time you take some medication and you're wondering how much of that medication is being retained in your body over the next 100 years, you can figure it out. So this is really nice and powerful here. If your common ratio happens to be in absolute value larger than 1, the infinite series does not converge. It will always diverge. And then we learned the important theorem of the divergence test. If a series converges, its corresponding sequence must have converged to 0. This is necessary but not sufficient. If a sequence does converge to 0, it does not guarantee that the series will converge. It's just that if the series converges, then you know that this thing happened in the past, that the sequence did converge to 0. All of these first 4 bullet points have to do with geometric sequences and series. This one is just general series. A theorem generally on series. Okay, what's coming up next? We're going to be talking about some convergence tests for more types of series, not just geometric series. What kind of tools do we have to tell if a series converges or diverges? All right, awesome.